This week on day 53, students will build and test prototypes of the products they've already designed to maximize or minimize thermal energy transfer. This lesson is best for students who are in person and can use classroom space and materials to build and test their prototypes, but students at home may also have access to materials they can use. Each member of the group should build and test their own prototype following the plan that the group designed in the previous week. However, if building a prototype is not an option, students have a couple of other possibilities. First, they can simply research the materials they were planning to use in their product and then explain why those materials will play an important role in the product. How will they minimize or maximize thermal energy transfer? Looking up the thermal conductivity of various materials can help students identify good conductors and insulators, or they could just search for a list of good conductors and insulators. Good conductors have high thermal conductivity. That means they readily conduct thermal energy from one place to another. However, students also have another option. On page 8 in the student handout, there's a link to a heat transfer simulator. This link takes students to the homepage for the Energy 2D Interactive Heat Transfer Simulation, created and maintained by the Concord Consortium. We've used some of their online simulations in past weeks to investigate thermal energy transfer. This simulation is a downloadable, open-source software application available to everyone and designed specifically with students in mind. Unfortunately, the software is not yet available online or on mobile devices, but if students have a computer, they can download a Mac or Windows version for free. Let's take a look and see how it works. After downloading and installing the app, open it on your device. The first screen is a blank blueprint-style workpane, similar to what we saw with Tinkercad. A helpful place to get oriented is the Examples menu. There are dozens of already made simulations across several topics. The topics that will most likely be helpful for students are conduction and convection. Comparing natural convection and conduction is a great place to get started. Here we see the screen split into two areas. On the left is a section labeled Air. On the right is a solid with a brick pattern. An area marked Insulator separates the two areas. And you can't tell right now, but underneath the entire thing is a heat source. Let's see what happens when the simulation runs. Right away, the heat source lights up. Convection currents spread out through the air on the left, while the bricks on the right slowly conduct heat upward. The thermometers at the top show the temperature just at those two spots at any given time, and a timer in the upper right-hand corner shows how much time has elapsed in total. Pressing stop pauses the simulation right where it is. It's a great feature for collecting data at regular intervals, for example, recording the temperature. The reset button resets the simulation to time 0 and resets all of the temperatures. So how does this actually work? Well, if we right-click on each feature, we can peek under the hood to see what's going on. Let's start with the insulator. If we right-click on it and select Properties, then if we go to Source, we can see that this insulator is not a heat source, and that its initial temperature is 0 degrees Celsius. Under the thermal window is where we get a lot of great key information. First, the insulator's thermal conductivity is at 0. This means it does not conduct heat at all. Although such a material doesn't exist in the real world, being able to create perfect insulators is a great tool for a simulation because it allows us to create simple closed systems and contain different features. Miscellaneous allows you to label different objects. Let's see what happens when we right-click on the solid. We can see that it is not a heat source and that its initial temperature was 0 degrees Celsius, but here under thermal we see some different numbers. The thermal conductivity is now 1 instead of 0. Next, let's look at the heat source that's down here. It's not labeled, but we know that's there because this is where all of the heat is coming from. Here, the key property that makes this a heat source is that it has a constant temperature of 30 degrees Celsius. If we wanted to increase the amount of heat that it was providing, then we could just increase this constant temperature. So let's make it 50, for example. And we see now immediately the simulation is getting hotter closer to that heat source. So this tells the simulation that this specific object should radiate a constant temperature the whole time that the simulation is running. If students are creating simulations to test prototypes that rely on heat sources, this feature is key. Let's take a look at a few other examples that might be relevant to students. Here are a couple of really common ideas around conduction that we often show students. First, two spoons, metal and wood, that are touching boiling hot water. This is really helpful to show us how different materials have different conductivity. And if we examine the properties of these objects, we'll see that the metal spoon has a conductivity of 1, while this wood spoon has a conductivity of 0.01. Another great example that might help students: which material is the best conductor? Students here can experiment with different materials to find out how different materials can affect the way that heat is conducted from this 100-degree heat source over to this non-heat source. If I press run, you'll see the heat source immediately starts radiating heat, and I can drag different materials to connect the heat source to this heat sink. Copper, of course, is an excellent conductor, and the heat quickly is conducted throughout the copper. If we look at its properties, we can see it has a thermal conductivity of 401. You can see the density and specific heat as well. These pieces of information are a quick Google search away, and these properties are what make the simulation a good model of things happening in real life. If we go to Industrial Applications under the example menu and then Solar Oven, we can see if students are creating or designing a solar oven. Here's a great way to simulate that using the sun. So the simulation not only shows conduction, convection, and radiation, but you can also, by clicking on the properties of the whole simulation, you can check sunny, and that will cause the simulation to rain down sun rays. The simulation also has some great earth science applications. For example, if we go to earth science and then sun and clouds, here you see different clouds and trees, and there's a graph overlaid on top of the simulation as well that's linked to this lone thermometer. If we press run, we'll see a sunrise. You can see the moon just changed to a sun up here. And we can see the sun rays changing angle, colors and lines showing us how the temperature above the ground is changing throughout the day as the clouds roll by. The trees also provide shade. And if we let this run for a while, you'll see a pretty clear pattern of a spike in temperature during the day, followed by a decrease at night, exactly as you would expect. So how can we create our own simulations? Let's take a look at some of the tools that Energy 2D provides. There are several tools and options across the top to draw different objects. First, there's a basic rectangle and circle tool. Next, we have a Polygon tool that looks like this capital letter I. And by clicking once, dragging, and then clicking again and again, we can create any kind of polygon with straight sides and angles. Double click to finish. Next is Blob, which is a tool for drawing, well, blobs, anything that has curved sides. After that is a ring. We can drop particles that will move with air currents when you run a simulation. And if you click the down arrow, you'll see there's also a particle feeder, which will spew out particles at regular intervals during a simulation, so you can track airflow. And there's also a fan, which can create air currents. Here's where you can also add clouds and trees. Next, there's the Thermometer tool, which allows you to drop thermometers to measure the temperature at any given location. Adding thermometers is a key feature in order to actually collect data that can be used to test a prototype. Remember, you can set objects as heat sources by going to Properties, Source, and then go to Constant Temperature. That way, no matter what is happening around that object, this object will emit heat at a constant temperature of whatever you say here. Remember that it's in Celsius. Making a new simulation from scratch is really difficult. It's going to require research into thermal conductivity, specific heat, and density of different materials, keeping in mind the units that are listed for each one. If students want to create a simulation from scratch, they're going to need a lot of guidance, and it's probably going to be easier for them if you simply provide the necessary parameters for the materials, those properties of each material. For students, it's likely going to be easier if they can find an example and then modify it, or use one of the examples provided in order to test a specific material or idea that's already related to their prototype. Energy 2D is a powerful tool, and it's incredible that it's both freely available and open source. I highly encourage you to explore the examples yourself. If students wish to use this great resource, be sure to work with them in order to help them develop a new model or use an existing model in order to test their prototype.